Good morning, everybody. We'll start this morning session with Monika Petr-Gotzens, who will tell us all about getting the most out of your observing time.
Okay, is this on? Yeah, it sounds good. So, good morning, everybody. So I will now continue from the point where yesterday's presentations had finished, which was how to write a successful ISO observing proposal. And we will assume that indeed it worked and observing time was allocated to your program. So now the aim of my presentation is to give you some guidelines how to optimally use this time. And I want to note that most of the following refers to service mode observations, but of course there will be also parts which are useful for visitor mode observations. So obviously as a PI, I mean, your overall goal is to obtain the data as soon as possible, to get all of the data. You do not want to have just half of the stacks for your Galaxy, for example. And of course, on top, it should be of highest quality. So the next step is to prepare what in ISO terms is called the phase 2. And the central point of the phase 2 is to carefully plan and prepare your observations by selecting the right strategies for your science case. So in principle, some planning should have also happened during your phase 1 when you were writing the proposal. But now you really must go over it again, and you should check for the following things. First, what kind of calibrations do I need? The best science observations are useless if you cannot calibrate it. So you should go and check what ISO provides you for free. And this is what ISO typically calls the standard calibration plan. These include things like flat fields, bias, darks, a photometric standard during the night. So you should really check if this is sufficient for your science or if you need something else. Because the something else, some special calibrations, you will have to prepare the observations for, and this time will also be deducted from your allocated time. The things from the calibrations from the standard calibration plan are for free. You don't have to pay for it. Okay. Then the next thing is to check if the instrument setup that you have indicated in your phase 1 proposal is still the best choice for your science case. For this, you should study very carefully the user manual, the template manuals, and if you find out, oh yes, there was something, right? Okay. So if you find out the instrument setup that I have indicated in my phase 1 proposal is not the one that really is the best, you will have the opportunity to change an instrument setup when you are preparing the phase 2, but this has to be approved by ISO. So carefully check it. Then it also could have happened that between the phase 1 and the phase 2, the exposure time calculator got an update. So it is really mandatory that when you start the phase 2 that you recalculate the exposure times with the exposure time calculator of your instrument and check again the signal to noise. For service mode, ISO has a lot of rules. I mean, a lot of restrictions, how to execute observations in service mode. These are typically things like, you cannot combine instrument setup X with instrument setup Y, and a very generic general rule, for example, for the service mode is that an observation should not last longer than 1 hour in total. So you have to check all these rules, and we provide specific phase 2 instrument-specific web pages for that. That's indicated here in the URL. And if you find out, oh, I have to break the law, break the rule for one of my science cases, then it could be possible that it will be allowed, but you have to submit a waiver, and ISO will then approve or reject it. Okay, so of course ISO provides many tools for observation preparation, and some of which are mandatory and some are optional. With these observation preparation tools, you will be able to design and plan and implement strategies specific for your science case. So I'm now going into details on how to decide on the different strategies. Very general strategic consideration are related to the rank class assigned to your run. As we heard already yesterday, your run is either allocated time in the highest priority rank, rank class A, which means that ESO will make every possible effort to execute the total of your program. So every OB should be in the end completed. Or your program got rank class B, which is a medium priority, also is okay. But for this rank class, you should know that maybe not all the observations that you have planned will be completed within the observing semester. And there is also the very important difference between rank A and rank B. Rank B runs, programs, will be terminated at the end of the period. So if only half of it was done, bad luck. Run A programs have the possibility to be extended to another period and maybe even to another period. So finally, we come to rank C class programs. This is the lowest category and it will in general be only executed if nothing from the rank A or rank B programs is executable at a certain time at the telescope. So this is why this rank class is also referred to as filler programs. And the call for proposal is also referred to as any weather programs, which in principle means bad weather programs. So now the rank class should a little bit determine also your OB constraints. A quick reminder, an OB is the smallest entity that describes your observations. The OB contains where to point the telescope, which filters, instrument setups have to be used, and how long to expose on your target field. And the OB constraints now define the conditions under which an OB is allowed to be executed. So that is, for example, under which maximum air mass, under which sky transparency, or what lunar phase and moon distance. And importantly, it also means under which maximum seeing or image quality is allowed for your observation, for your OB, is acceptable. So you use the P2 tool to define these constraints. In principle, these constraints are not completely free. I mean, you have not a free choice, for setting the constraints, because in the phase 1 proposal, you already indicated, okay, I need 0.8 arc-second seeing or 1 arc-second seeing, and I need dark moon or full moon, whatever. So these constraints that you had specified in the phase 1 proposal are binding. You cannot have better constraints in the phase 2, but you can relax your constraints in the phase 2. So if you had asked for example, for 0.8 arc-second seeing, and now you find yourself in the situation where your program was assigned rank class C, then you should consider to relax, for example, the seeing constraints. So it is also very important that you define realistic constraints, and even more important that you define constraints realistic for your rank class, because these constraints will determine how much chance of execution your OB will have. And obviously this is not, obviously there's not an infinite amount of time available in photometric conditions with 0.6 arc-second seeings, right? So let's look at these statistics of seeing distribution over the year. So in these plots, you see color-coded the probability of a certain seeing realization as a function of the months. And the thin black line indicates a 50% chance in those plots. So, and for example, if you need for your science case a seeing of 0.6 arc-seconds and clear of photometric conditions, then you can read from the plot that this condition typically occurs 20 or at most 30% of the time, so which is a very low probability, right? If you are in rank class C, then this is probably not a good choice, because if we do have these conditions at the telescope, it's most likely that it will go to the A-ranked programs. Yeah? Or similarly, if you are here up here, if you say, okay, my seeing condition can be up to 1.2 arc seconds, then you are more in, and I also can live with SYN conditions, then it's almost 90 or sometimes 100% of chances that it can be executed. So also think about if you really need dark sky, so maybe gray sky or full moon conditions are okay too. In this plot here on the left, you see as in the red line, the sky emission during dark nights, so no moon, and in blue you see the sky emission for full moon. And it's very obvious that in the optical, here in the V band, there is a huge difference in the sky emission. And of course, if you're observing in the optical, the sky constraints make a big difference. But please also see that if you are going to the near infrared, right, it really does not make any difference if the moon is shining or not. So do not over constrain, for example, your K band, H band, J band near infrared observations by putting fractional lunar illumination of 0.5 or 0, right? So this would be not a good idea. You can also make use of what we now call the twilight constraint. I don't have a plot for that, but it essentially means that the sky, the night sky at K band is already dark even before the twilight has ended. So you will not see any changes in the background counts in your K band 10 minutes before twilight has ended, or even 20 or half an hour before twilight has ended, and after the twilight has ended. So you can set a constraint in your OB which allows the operator to start your OB even before the evening twilight is officially over. So this other plot here shows how the brightness of the sky depends on the position of the moon. Okay, here in this example, there is the moon is at low at the horizon, has half full. Okay, and as you can see, the darker the sky, the darkest sky is actually on the order of 60 degrees away from the moon and not 120 degrees away from the moon. So this is a typical, yeah, it's interesting, right? But this is a typical mistake people make. They say, okay, I want an FLI of 0.5, but then I put the moon distance constraints to 180 or so. It doesn't help you. I mean, it's even not a good idea. So, okay. So, then I show you in the next slide a few typical examples of reasonable OB constraints for the different rank classes. I mean, for A rank, there's not much to say. I mean, here you can, in principle, put indeed the constraints that you need for your science. You do not have to be specifically restrictive. If you want 0.6 arc second seeing and gray time, this is probably fine. So for rank B, yeah, you should consider maybe to relax the original constraints a bit if this will still be okay for your science cases, because remember that at the end of the period, the OBs will be terminated, and that was it. So I think most of the advantages, or let's say advantages of playing with the constraints is in the rank C class program, where even though in the phase 1 proposal you have asked for example, 0.8 arc second seeing, but now you end up in rank C, then you might consider maybe dropping a few of your targets, relaxing the seeing to 1.2, use the exposure time calculator and check how much longer do I have to expose under these worse seeing conditions in order to get the signal to noise that I need for my target, okay? But it probably pays off because you will then, in the end, get half of your targets done instead of probably nothing if you keep very stringent constraints for the rank C. So next point, your observing program was allocated only a limited amount of time. So use it efficiently. In case your run is assigned rank class B or C, it's even not likely that all your observations, all the OBs will be executed. So with the P2 tool, and Giacomo will give you a demo after my talk, you can assign a priority of execution to each individual OB. And this can be very useful if your set of OBs, for example, consists of observing one target at different filters, and you know that with the K-band filter, for example, you can at least do some science. So give this OB then a higher priority than the other OBs. With P2, you can also implement different execution strategies. And quite powerful is the use of the so-called concatenations, which in P2 is recognized by this purple symbol here. It means that two OBs are executed in immediate sequence. And two or more OBs, right? It does not have to be necessarily only two. And you can use this, for example, for short OBs that are observing targets close together on the sky. And short, I mean maybe the total execution time is 10 or 20 minutes, to put them in a sequence, because this will save you a lot of time in the telescope slew, right? So you can also use this concatenation strategy to attach a calibration OB that scientifically must immediately follow your science OB. And depending on where the targets are on the sky, you can save up to 5 minutes per OB with this kind of strategy. And if you have 20 targets, you can maybe in the end put another 2 or 3 targets. So next strategy is the time sequence. If your science case is to observe variable events, then you want to have observations at certain epochs. And this can be implemented by the so-called time link container, this yellow thing. So you should use it probably for B-ranked programs, because I mean, it would be a plus, it would be an advantage, because it will put an additional priority boost for OBs that have to be executed at a certain time. For C-rank programs, it's less of a good idea, because these are only considered if nothing else can be executed. So I would even say for C-rank programs, you should not put any time constraints. The next strategy concerns grouping of OBs. That can be useful if, for example, you have different targets, and all the targets shall be observed at a certain filter sets, JHK, UBI, whatever. And it is for your science more important to have one target completed than having many targets with just one filter. Okay, so then the group will help to boost the priority of execution for those targets that have already been started. And this is also particularly useful for B and C rank programs, but in general, it's a good strategy. You should also use it with Class A programs. The finding charts are more important than you might think. Okay, it is not too rare that we encounter the situation that an OB is started at the telescope points, and the field doesn't look at all like what is shown in the finding chart. So in these cases, the OB is aborted, and unfortunately, your chance of executing your OB is lost for that moment. So this is particularly a pity for observations that request very good conditions, which are rare, right? So you have missed this chance, or for OBs from a C ranked program. Another example is given in this finding chart, which shows 2 bright stars. And let's assume the README file instructions say put the bright target under the coronagraph. So it comes to the telescope and the operator sees that. And then of course he or she asks himself, so what is a bright star? Is it this one or this one? Okay, this one is maybe a little bit brighter, but they're both bright, and this one is actually more in the center. So this is a bad finding chart. And again, the person will probably abort the execution of the OB and then ask, we have to go back to the user. So what you should do is to encircle the one that is actually the target, or to make an error, or whatever use you can think of to really indicate it very clearly. So now we come to more instrument-specific recommendations. There are several instruments that offer multi-object spectroscopy, and these are force, KMOS, and flames. And there are specific observation preparation tools to optimize the positioning of the fibers or the slit mask precisely on the target. So the success of your observations depends crucially on the astrometric accuracy of the target input catalog. So you should really take special care and take your time to fine-tune the target input catalog. You must also make sure that the coordinates of the reference stars, which are often used for the acquisition in multi-object spectroscopy, are also in the same astrometric reference system as your targets. Some other instruments, in this example it's Visier, perform spectroscopy on targets that are that faint that you cannot see it in the acquisition, as for example here this invisible target in the center of this yellow slit. Okay, so in those cases you should define a nearby bright star as an offset star, so like this star here in the example, and this tool, the GuideCam tool, will then calculate the correct telescope offset that is needed in order to bring your target into the slit after the acquisition on this offset star. So the use of this tool will then automatically calculate what we call the blind offset values in arc seconds, and this can be even transferred without your manual interaction to the OB that you are preparing in P2. Okay, so this is very powerful to use such a tool because it avoids possible mistakes that you could make when you prepare your OB, maybe a wrong sign, right, in the offsets, and that would then result in a loss of data or useless data because you would be integrating for an hour on something which is not there, I mean, on the wrong position. Another example is the selection of a tip tilt star for the adaptive optics mode of Muse that is also facilitated by using the GuideCam tool. Using GuideCam also allows you to visualize exactly where your field of view will be placed, and if your main target of interest, so here in this example, I assumed it's maybe a star-forming region in this galaxy, is exactly well covered. Okay. So, as a last example for using GuideCam as your observing planning tool, I show here how one can very nicely visualize the field of view offset pattern. In this case, it is for the Hawkeye imager. So you can play around with the offsets until you exactly cover the fields. For instance, here in this example is the outer part of a globular cluster that you want. Okay, and then you can extract from the control panel of this tool the precise offset values, the ones that you have to put into the observing template of your OB. Again, this is very useful to avoid bad surprises when you retrieve your final data, because you can be sure that the tool gives you the right values. Good. Last but not least, you should use the user portal service to monitor the progress of your service mode observations. In the phase 2 section, you will find a link that's called Check the Status of Your Observing Run. And this link will bring you to a summary table with the list of OBs that were already executed. So here, this is the list of OBs with the OB number. And via this link, you can even connect to the raw data in the archive. And it's very, very important that you check the obtained data. Imagine there is a mistake. I mean, the field of view is slightly not where you wanted it, or the wrong target was put on a slit. And if you notice this mistake immediately, you can tell ISO and correct for this. Yeah, so you can then, of course, update the remaining OBs and so avoid that all the remaining OBs on the same target might produce useless data. So this is actually very important to do it in real time and send wild real time. So very quickly. Similarly, you can check the status of your time-linked OBs. So this shows the overview in P2. Here are the OBs. This is the status. For those that could not be executed during the epoch that was foreseen for the execution, the OB status goes to failed. Here, these little Fs, right? You can, according to the ISO rules, that's what we offer you, you can create new OBs for the ones that have failed and add those OBs to the end of your time sequence, if this is scientifically still useful. So again, you should check this quickly, right? 6 months later, it's too late. Then we will not add anything because maybe the period is already over. So, and this brings me to the end of my presentation, and I think I leave you with a summary, and thanks for your attention.
Thank you very much, Monika, for a very nice talk. Do you have questions? Do we have questions from one of our...
There was one.
Yes, can you use the microphone?
So for the OBs that were not executed correctly, will they be re-observed, or
yes,
every correction will be applied only to the new OBs?
No, they can also be re-observed. So it depends a little bit on what was the problem. For example, I mean, if the operator put the wrong target on the slit, of course we re-execute it, we put it back into the queue, right? If after already 5 OBs were executed because you made a mistake in the coordinates, then it will be, well, could, I mean, then we have to consider the cases. Pardon me, Ed? Yeah, exactly.
Any more questions here?
I would like to ask what is the reaction time for a waiver? If you would like to.
Yeah. So usually it's within it should be within, it's 1 week, yeah, exactly. So two days apply to the tickets. So it's usually 1 week. But you have, if you need a waiver, you should submit the waiver at least 1 week before the phase 2 deadline.
Okay, and
of course, this like similar to Nando's show yesterday, where everybody submits in the last 10 hours. This is similar to waivers. I mean, we sometimes get waivers an hour before the deadline. I don't want to encourage you to do that, but but we will not reject them. I mean, it will then, but in the last 3 days before the deadline, it will take longer for us to deal with it because we have a lot.
I have the other question. If you have, for example, accepted program, you observe the supernovae or novae, and you find that your object unexpectedly goes much fainter than you predict, and in this case, you need to increase the OBs over the 1 hour, so you can submit some kind of request.
Yes, absolutely. I mean, so that's a very typical, very often we get the request of exceeding the 1 hour, and this is in most cases it is okay up to 1.5 hours execution time. If you want to have a waiver for an OB to take 3 hours, Then it will also depend, I mean, if you're in rank class A, rank class B, rank class C, because for example, in rank class C, we typically don't grant continuous execution of 3 hours, because that would mean that it could take away time from A ranked and B ranked programs. So it depends again on the case, but yes, if the OB is 1 hour 10 minutes or 1 hour 15 minutes, that's usually not a problem.
Okay, thank you.
Any more questions for Monika? Any questions from our participants online? If not, let's thank Monika.